Hello, am I audible?
Yes, sir, you are.
Okay.
Yes, sir.
All right. Yeah, thanks. Okay, so I hope you're all able to see this. Let's see the slide.
Yes, sir.
Yes, sir.
Okay, so what we'll do is for CT, we'll have three revision sessions. So one is today, which we'll do weeks 9, 10, and 11. And the other session will take care of weeks 1 to 8. And finally, next week, I think we'll have some problem solving sessions by looking at previous year question papers, right? So that will happen. Now, today it will be exclusively for graphs and recursion, right? So that's what we'll do. Now, the plan is I'll just quickly go over some of the basic ideas in graphs, right? And then we'll look at a few problems, right? So few problems, illustrative problems that show how to manipulate graphs in computational thinking, right? So that's the agenda for today. So let's get started. So this is the way it'll work is I'll just either have some problem description on the screen, or there'll be an empty piece of code which will be slowly filling up one at a time, one line at a time, and it'll be basically studying a lot of code snippets, right? That's what we'll do today. So we won't do question and answers like they appear in the end-term exam. That will be done, as I said, next week. Today it will be more of understanding the code and how things work, right? So that's what we'll do. So the first snippet of code that is there in front of you, it is doing something, right? So can you tell me what it is doing? Have you seen this code before? This piece of pseudocode?
Sir, it is the dictionary.
Okay, there is some.
It is creating a matrix.
Okay, what kind of a matrix is it creating? I mean, is there something special about the matrix it's creating?
The values are all zero.
Yeah, all inclusive.
Okay, so it's an empty, so like zero matrix, right? It's creating a zero matrix. So have you learned something similar to this in the course?
Create matrix in
Adjacency matrix.
Right. So this is nothing but create matrix. I've just changed the name of the procedure so as to see if you're all able to identify this. So it's the same thing, right? I just changed the name to do something. So create matrix is what this is, right? So this is the first thing that you need to understand. What is this doing? It's initializing an empty dictionary. Okay, mat is an empty dictionary, and then rows and columns here represent the number of rows in the matrix and the number of columns, right? So that's what they represent. And the outer while loop is for the rows, right? So every iteration of the outer loop will end up creating one row of the matrix, right? And once you enter this loop, what do? You initialize another empty dictionary, right? And this is a dictionary of dictionary, right? So it's nested, and then you keep filling the columns one at a time. So for the inner loop, the job of the inner loop is what? It's to keep adding zero
columns to it.
Yeah, so its job is to add an entire zero column of zeros, right? Or so that's what it does. And you keep doing this, you end up getting a matrix, right? So what will be the dimension of this matrix?
So it depends on the parameter we pass as
Into
rows and
columns.
columns.
Right.
Rows
So in
into
general,
columns.
yeah, rows into columns, right? So rows cross columns. So if you call it on say 3,5, it'll end up creating something like this, right? So this is the important part. The other part is, unless in other ways differently specified, we always start from zero, right? So the rows are always indexed from 0 and the columns are always indexed from 0, right? So if you have a create matrix 3 comma 5, then it will create a 3 by 5 matrix. But if you want to index into the matrix, you have to use 0 indexing, right? So just like a single list starts indexing from 0, right? So you have a nested dictionary here, and we have chosen to index from 0. We could have chosen otherwise also. We could have chosen 1, 2, 3 and 1, 2, 3, 4, 5, but this is a convention, right? So if we had wanted to do 1, 2, 3 and 1, 2, 3, 4, 5, which two lines of the code should we change? We want 1, 2, 3.
J, y
zero
equal to
and
z,
j equal
I
to
equal to 1, j equal to 1.
Okay, is that all? Is that the only thing you need to change?
Yes, sir.
Okay. So if I change I equal to 1 and j equal to 1, it will give me it will still give me a 3 by 5 matrix, or will it give me something else?
Rows
row-
plus
one
1,
row,
columns
five
plus
column.
1.
Right. So you have to change this, right? The condition also has to change. So if you make I equal to 1, then I should be less than or equal to rows, or alternatively, I should be less than rows plus 1. Right. So depending on how you choose your initial condition, basically the loop has to go through 3 iterations, right? 3 iterations. The outer loop will go through 3 iterations, and the inner loop has to go through 5 iterations. Okay, so that's the basic thing, right? But anyway, let's not confuse ourselves with that. We will always start with I equal to 0, j equal to 0. Okay, so is this create matrix clear to everyone?
Yes, sir.
Okay, so now
Yes.
we'll go ahead and assume that you are given a graph like this, right? So how will you populate, rather I should have made this populate the matrix, but anyway, so how will you populate this adjacency matrix? So first of all, what will be the first line of code that you will write?
Key lines. So we have to find the keys of this node.
There's an x from 1 to 0. So matrix of 1, 0 would be 1.
Okay, but even before that, right? So where will you get matrix from?
Create matrix.
Create matrix.
Okay, so
matrix.
what should be the parameters?
N, so if it's a graph, we
Create matrix of
3 into 3?
3,
yeah 3 comma
So
3.
3 comma 3, right? So it will be 3 comma 3. So you'll create matrix with parameters 3 comma 3. Now, one important point is this, right? So when it comes to graphs, when it comes to the adjacency matrix of a graph, will you ever come across a situation where you have create matrix of A comma B with A not equal to B? Will you ever come across that kind of a situation where the two parameters are unequal?
No, sir.
no, sir.
No, sir.
Right. So always when it comes to graphs and when you're creating an adjacency matrix as opposed to any random matrix, you'll always have n cross n, right? So in this case, it's n is the number of nodes. So you'll end up creating 3 cross 3 matrix here. Okay. So assume that you have created the 3 cross 3 matrix. Now, how will you modify it so that it becomes the graph? It becomes the matrix for this graph.
For each I in rows,
If there is an edge between 1 and 2, then we will update 0 to 1.
In this graph, matrix of 1, 0 would be 1.
Okay.
Matrix of 0, 2 would be 1.
1,
And
2,
matrix
2
of
will
2,
be
0
1.
would be 1.
Yes.
so
Okay.
it's a directed graph, sir.
Right. How many such updates you'll do? What will be the total number of updates you'll do on the matrix?
4.
4.
Right. Right. So you first create matrix of 3 comma 3, and then you do 4 updates, right? So if you can proceed systematically, so start with 0. So 0 is connected only to 2, right? I mean the edge from 0 outward edges from 0 are only 1, right? So 0 to 2. So mat of 0 to is 1, and then the outward edges are 1 0 1 2 for 1, and then for 2 it is just 2 0. Okay, so you could have gone the other way also. You could have looked at the incoming edges. So you can, focus on 0 and ask what are the incoming edges, right? So then 0 will become the second index, and then mat of 1 0 is 1 and mat of 2 0 is 1, right? You can do the same thing, but rather than looking at outgoing edges, you can look at incoming edges, right? So there are like two ways of thinking about this. So this much you must know. And this is the matrix, right? So it's simple enough. Now, here is the catch, right? So actually, what is mat? So what does create matrix give you?
A nested dictionary.
It's a nested dictionary, right? So now, should we look at this? There might be this confusion, which I realized in the last session, between the nested dictionary and the matrix, right? So there were quite a few, I felt there was quite some confusion between moving between these two things, right? So please note this equivalence or this relationship. This nested dictionary is the same as the matrix. Okay, of course, create matrix is going to give you this nested dictionary, right? So let's go over this nested dictionary and see what it's doing. So 0, 1, 2, 3 are the keys of the outer dictionary, correct? So 0, 1, 2 are the keys of the outer dictionary. And for each of these keys, you are going to have an inner dictionary, right? So same keys, 0, 1, 2. Okay, and the value is going to be what? It will be indicative of
Edges,
right? So if there is an edge, that particular value will be 1. If not, it will be 0. Now, you can choose to think of the matrix like this. Visually, you can think of it like this. It's not wrong. But why would you do something like that when you have a very nice 2D representation here? Okay, it's the same thing. So when you say mat of 0, 2, okay, when you say mat of 0, 2, in the matrix, what are you doing? You're looking at the 0th row, second column, right?
yes.
In the dictionary, what are you doing? You're looking at key 0,
First 0.
and then
another key 2.
another key 2, right? Now, it's the same thing. So you can actually, whenever you're dealing with the graph, with the adjacency matrix of a graph, you must know that it is ultimately a nested dictionary. That's fine, but keep it in the back. Keep it at the back of your mind. When you are manipulating a matrix, think of it as just this matrix alone, right? You don't have to think about it every time as a dictionary, right? So that's something I want you to keep in mind. So know this representation exists, but then whenever you're dealing with an actual pseudocode involving graphs, you can always comfortably stick to the matrix. Okay, is that fine? Is this understanding clear?
Yes, sir.
Okay, so now let's look at the other elements of graphs, right? So once you have an adjacency matrix, now you of course need to iterate through the matrix, right? So you need a way to go over the elements of the matrix. Now you could do it in the following way. This is what we follow in our course, right? So you take the keys of the matrix, okay, like we saw before. Keys of the matrix are 0, 1, 2, right? And since the dictionary is going to return your keys in some arbitrary order, you sort it. Okay, so you assume that there is some procedure which sorts the list. Okay, so the list will be sorted. So you'll end up getting 0, 1, 2. So for columns, what do? You take mat of 0, right? If you go back, mat of 0 is what? Mat of 0 is this dictionary, right? So that will also have some keys. So the same keys, in fact, will have same 0, 1, 2 as the keys. Now you sort them and you get 0, 1, 2. Okay, so whether you do rows of mat or columns of mat, for an adjacency matrix, the result will always be the same. Okay, so this is an important point. Whether you do rows of a matrix or columns of an adjacency matrix, whether you do one or the other, you will ultimately end up getting the same list. And the list will be what? 0, 1, 2, so on till number of nodes minus 1. So in general, if you have n nodes in a graph, okay, if you have a graph with n nodes, rows of the adjacency matrix will be this. Columns of the adjacency matrix will also be the same thing. Okay, is this fact clear? Because sometimes we'll use rows of mat, sometimes we'll use columns of mat, sometimes we may even use columns of mat when we should have actually used rows of mat, but then it doesn't make a difference because both of them return the same list.
Yes, sir.
Sir, can you explain the column of mat, how we are getting there?
Yeah, so see the column. So if you want the column, what is the column? Columns are the inner dictionaries, right? So they are representative of the columns, right? So this is what, if mat is the entire dictionary, mat of 0 will be what? This inner dictionary. Now, what you are asking is, show me the keys of mat of 0. So show me the keys of this inner dictionary. So those keys will be what? 0, 1, 2 in some order. And you are just sorting them. So sort of keys of mat of 0.
Sir, sort will give us keys in ascending or descending order.
It will give it in ascending order, right? We assume that, of course, sort, depending on how we write it, it could be ascending or descending, but we are assuming that the procedure here gives it in ascending order.
Okay, sir.
Okay, so any other questions about what rows of mat and columns of mat are doing?
Yes, sir.
Hello.
Yeah.
So if sort of key of mat 0 is giving the key values of 0, then why we are getting 0, 1, 2? I'm
So
not getting this.
so we are not, it won't give us the values, right? It will see. What is mat of 0? It is this
Dictionary.
entire thing, right? The whole thing.
Yes.
Okay, so the whole
Yes.
thing is what? This is itself a dictionary, right? So this is itself a dictionary. Now, what are you asking? You're asking what are the keys of mat of 0.
Mat of 0.
So that, what are the keys of mat of 0? They are 0, 1, 2.
Okay. Okay. Because in rows we are not giving mat of 0 and we are getting 1, 2, 0, 1, 2, and for column also we are getting the same thing, but we are not putting the argument 0. So
Uh,
that's my question, that
yeah,
the
so
code
in,
is changing and we are getting the same answer.
yeah, the code is changing, but fortunately for us, the outer dictionary and the inner dictionary have the same keys, right? So this is what I was talking about. In an adjacency matrix, it will always be a square matrix, right? So every row will have n columns associated with it, and there will be n rows, right? See, there are 3 rows here, and there are 3 columns associated with each row.
Yes, sir.
Therefore, there will be 3 outer keys and there will be 3 inner keys. Therefore, even though your code is changing here from keys of mat to keys of mat of 0, it doesn't matter because you have the same number of keys in both the cases.
Okay, thank you, sir.
Yeah. So not just
So,
the
sir,
same number of keys, but the same keys.
Okay, so sir, if I use mat of 1 instead of mat of 0, I will get the same result, right?
Exactly. Yeah. In fact, sir mentions this in his slide, right? So you could use mat of any row, but you choose to use mat of 0 for convenience. I think that's all.
Yes, sir. Thank you.
Yeah. So you see, now what you can do is you can bypass this. You don't necessarily need to remember what this is, because rows of mat are giving you the rows, list of rows. Columns of mat are giving you the list of columns, right? So we can kind of ignore this for now, right? So that's the idea. Okay, so now let's go ahead, and we have all the things we need to solve some simple problems. Let's look at the first problem, right? So we have to find the number of outgoing nodes, right? Number of outgoing edges. Sorry, not nodes, but number of outgoing edges from a given node in a graph. So we have to complete this procedure. Okay, so procedure out degree, what it does, given a node, let's say 1, it's going to find out how many outgoing edges it has. So in this case, there are 2, right? So 1, 0, 1, 2. So it should return the answer as 2. So what is the first line of code that you will write?
For each j in columns of I. Uh,
Sorry.
if for each j in columns of I, if I j equal to 1 or n equal to n plus 1.
Okay. Right. But even before that, right? So what will be the
If I have to initialize the variables n equal to 1 and yeah.
Okay, but yeah, what is the very first line of code that you will write? So when you're trying to count something, what will be the first thing that you do?
Count equals to 0.
Okay, something you are counting, right? So you will
Yeah.
set, let's say it's out degree that you are counting, right? So you'll set that to 0. Now, right now you will have a for loop as you mentioned. So I'll put that for loop in here. So for each column, each C in the columns of graph. Okay, now let's take one, right? So for each C in the columns of the graph, what should you do?
If C,
Then we have to check the rows.
We have to write for each R in column graph, right?
For each
Rows
R
of
in the
graph.
rows of
Rows of
the graph.
if RC
There is
equal to 1,
if RC
equal to 1, then out
to
degree
1,
equal to out degree plus 1.
Yeah.
Okay, so tell me, should I write columns of graph or rows of graph here?
No,
It
next
doesn't
lines.
matter, sir.
It doesn't matter, but just to be, absolutely correct, right? The outcome will be the same.
For each R in rows of graph.
Okay.
For the next one.
Are we iterating through the rows of the graph or the columns of the graph?
So right now we are iterating through columns of the graph, but if we have to find out the
mat of C, sorry, graph of C, column C. For each R in column
rows of C.
Graph of C, right?
Okay. All right. So I'll go and fill this and you tell me if this makes sense or not. So for each C, I'm going through each column in the graph, right? I'm not going through each row. I'm going through each column in the graph. If there is an edge from the node to that particular node C, right? Node to C, if there is an edge, what am I doing? I'm increasing the out degree by 1.
Yes.
Okay. Now, and then I'm returning out degree, right? So now, is this code correct or not?
Yes, sir.
Okay.
Sir, are we giving a node as parameter in this procedure?
Yeah. Node is a parameter, right? So we want to find out how many edges go out of the particular node, right? Node is the parameter. So for example, 1.
So initially now we are taking 1. Okay. I thought we have to iterate through the particular each and every nodes now.
We are iterating through each and every node, but then.
So we are not iterating through each and every node. We are just iterating through columns of that node. I mean, then.
Yeah.
Well, we are iterating, right, through each and every edge connected to.
Yeah.
That could possibly be connected to the node.
But we are passing a parameter node, right?
Correct. So we want to find out how many. Say, for example, let's take node is equal to 1. We want to find out how many edges go out of node 1. Right. So that's what out degree is, right? So for out degree, you need to specify how many which node you are interested in, right?
Yes.
That's right. Yeah.
Okay. So I'll just show this one example and it will be clear. So see, these are the columns, right? And these are the rows. Now
that's right.
Here we are actually going over, well, depending on how you look at it, we are going one column at a time, right? So we are at a particular row. We are at row 1. Okay, we are at row 1, and then we are skipping one column at a time. That's why I've written for each C in columns of graph. Okay, so I'm looking at the 0th column, then I'm looking at the first column, then I'm looking at the second column, right? For a given row,
That's
right?
Yeah.
So out degree of graph comma 1, right? So we are calling this procedure on this graph on the node 1. Okay, so out degree will be initialized to 0, and then you come to this for loop. So the first C in the for loop is 0, right? So will this condition be satisfied?
No,
1
sir.
0 is it 1 or 0?
1 0. 1 0 is satisfying, sir.
Oh,
Satisfied, right? So out degree will become 1 now, right? So out degree will become now. And then we move to C equal to 1.
It
Okay.
will not satisfy.
It will not satisfy. So we'll go to the last column in the graph. And then what will happen now?
It will increment out.
It will increment, right?
Increment again.
So it will get incremented. Out degree is 2. Now what will happen?
It will return out.
It will return.
It will return, right? That's the end of the loop. And then outside the loop you have return out degree. So now can you tell me, was it appropriate to write for each C in columns of graph?
Yes.
That's right, sir. That's right, sir.
Okay, so this is appropriate. Of course, like all of you mentioned, it would have been okay if we had written for each R or C in rows of graph, because it will give you the same result, but then it's more appropriate to write columns, because you are fixing the row because we are looking at the out degree. The edges that go out of a node, we are fixing rows, and then we are moving one column at it. Okay, does anyone have any questions so far in this example?
Sir, in this we can go by rows as well. If we want all the out degrees, it's just not the node of 1. So in such case, we can write R, isn't it, sir?
If you want to compute every row degree, then you'll have a nested loop, right?
Yes, sir.
Yeah, in that case, you will have to go through, you'll have an outer loop which says for each R in rows of graph, and then you will maybe store the out degrees in, say, a dictionary, right?
No, yes, sir. So you said if we go by that approach as well, like we all said like for each R. So if we go by that approach, the output won't be same. That would give for every node out degree. And this is precisely giving the out degree of the node we have mentioned.
Okay, so yeah, so I when I said what you have mentioned, I thought you all mentioned for each C in, say, for each R in rows of graph, do the same thing.
Graph node R equal to 1.
Okay, so I thought that's what you all meant. Node of R, instead of calling this columns, if you were to change it to rows, the output will still be the same, right?
Yes, sir.
No, in that case, it would be same. But if we are doing the nested loop.
Yeah, nested loop. Yeah, you're right. Then it won't be same.
So like everyone were saying, like after this code, after this line, we were mentioning like for each R. So
okay. No.
Totally give the different output.
Yeah. So you should not. This doesn't need a nested loop, right? So this only needs a single pass through the. This only needs a single pass. Right, any other questions?
Yeah, sir, I had a doubt here. The node is 0 will correspond to row 0, right? If the graph is different, say it's instead of 0, it's 1, 2, 3. How can you give graph of in the matrix the index as node C? Because then corresponding to the vertex 0, it won't be the row 0, right?
Then we can assign those nodes to, we can assign those rows and columns to those nodes. Say if you have
or we can do node minus 1 as well.
No, if you have ABC as your nodes, then you can assign those ABC to those nodes, 0 to A or some other node. That can work as well.
Yeah, so your question is, the node is labeled differently, what do we do? Is that the question?
Yeah, sir, because here the 0th node corresponds to row node itself, right?
0th, can you come again? 0th?
Sir, here the node is 0, and for that all the vertices we have will also correspond to the row 0, right? Because we've given a graph of node C.
Right. Yeah. So see, the labeling is kind of immaterial, right? So how you label them is not too very important, right? So if this were to be a different label, then that will reflect here, right? So instead of calling it I could call it, for example, C1, say C1, C2, C3, or C0, C1, C2 instead of just 0, 1, 2. This is quite, this is agnostic to how you label it, right? Graph of node C is going to iterate through the columns.
Okay, it's a nested dictionary. Okay. So, sir, in a matrix, the indexing default is not from 0.
In what matrix? In a, okay, in a normal matrix, right? In the matrix that we are used to in mathematics, you're saying.
Normally, for a matrix, the indexing starts from 0, right? So that's why I got confused. Yeah, I think I got your point.
Okay, so normally, you see, in a general matrix that we deal with in mathematics, it starts from 1. Okay, but in CT, what we have done is we have indexed it from 0, right? It starts from 0. I hope that is.
Got it. Yeah. Okay,
Yeah. Okay.
Thank you. Thank you.
Okay. Fine. Okay. So similar to this. Okay. So we iterate through the columns and then we update the out degree. We return it. Now let's do this for in degree. So how will the code change for this? In degree is the incoming node, incoming edges, right? So
Yes. For each C in columns of graph, if node if
So
C
can we
node,
in the previous question we had like node and C. So we can
C
just
node.
change C to node, like
Yeah.
node to C.
Yeah,
C node equal to
1.
can
freeze the columns now.
right. So we are freezing the columns. That's correct. Now I'll call this in degree, right? Similar to the previous one. This instead of out degree is in degree, and then you finally return in degree. In between, you have to compute in degree, right? So you said for each C in columns of graph, that is not wrong, but is there
we
anything
can
else?
write for each row R in rows of graph.
Yeah, that will be more appropriate.
If R node equal to 1, we increment in degree.
Correct, right? So that's more appropriate. So we are finding all those edges which come into a node. So we are looking at one column of a node. Rather, we are fixing one column and then we are going row by row. Okay, so for each R in rows of graph, if the edge that is coming into the node, right? So graph of R node is W equal to 1, in degree is incremental. Okay, so let's look at this time. Let's look at in degree of graph comma 0, right? So 0 from the figure here, we can see that there are two incoming edges, right? So 1 to 0, 2 to 0. So if you look at the graph, the matrix, so you look at column 0, and then what comes to 0? So 0 to 0, there is no edge. 1 to 0, there is 1. 2 to 0, there is 1, right? So you go this way. Okay, is that clear to everyone? We are iterating through the rows.
Yes,
If you
sir.
are in degree.
Yes, sir.
Okay, and in the end, you're
Fixing
fixing the-
column and moving through rows.
Yeah. Okay, so that's the out degree, in degree part, right? So that will, here again, your in degree. Okay, so next question is regarding graph being directed or undirected, right? So let's start with the procedure which returns true if the graph is undirected, otherwise it should return false. Okay, so it will accept the adjacency matrix as input. If it is undirected, it should return true. So what is the main thing that you will check for?
So whether for graph ij equal to 1 and ji equal to 1 as well.
No. We should check like ij should be double equals to ji.
Yeah, like
Yeah.
if for every
The same
ij there is a
If-
node for both the cases. I mean, if ij,
It's the same
like,
thing.
Like mij
If
It
the-
has to be
equals to Ji.
symmetric matrix.
Ha,
to
symmetric
be an
matrix.
undirected graph.
Okay.
So we have to iterate through rows and columns as well. And then we can check the condition as ij is double equals to ji.
Ji.
Okay, let's see. So you have for each R in rows of graph and for each C in columns of graph. If there is an edge from R to C, and or like, I mean, that's not necessarily the case.
So
See
we
here
have
to
return false. False.
Return
value.
false.
return false, right? So if so there are two conditions here, right? So there could be an edge from R to C, and so graph RC could be one, and then there may not be a corresponding edge from C to R. Correct? So
Yes.
if in that case you have to return false, right?
False.
And then if you are convinced that for every pair of vertices R comma C, if there is an edge from R to C and there is also an edge from C to R, then
return true.
you just return true, right? So this is again, as you all mentioned, this you can also view this as checking if a matrix is symmetric. Okay, so if it is not symmetric, return false, and if it is symmetric at the end of all your computations, return true. Okay, so this example here is directed, so we have to get false. Now, how many iterations of the loop will happen before you detect that it's a directed graph?
Can you repeat the question, sir?
So, how many iterations of this loop, either outer or inner, right? Or you could tell me both. After
One,
how
sir.
many such iterations will I be able to detect that this is a directed graph?
After first
N
iteration,
cross
it will
N?
return false, sir.
Is it N cross N?
Okay, not in the general case. I'm asking in the specific case.
9
Yes, sir.
for this can be 9.
Okay. Sorry, what all answers? I got multiple answers. Can you tell me 9 was one and then 1 was, I think, an answer?
Yes, sir.
Any other answers?
6. 6, sir.
Okay.
N
Yes,
into
sir.
N minus 1.
Okay, let's see. So this is the first offending pair, right?
Yes, sir. Yes, sir.
So let's see how it goes. So when R is 0, it will start with R being 0, right? So when R is 0 and C is 0, it's not false, right? The RC is CR. Basically, you are looking at the diagonal element, so you are safe. Now R will stay. So one iteration is over, right? One inner iteration is over. Now when you come to the second inner iteration, R is 0, but C is 1. Correct?
Yes, sir.
So 0, 1 and 1, 0 you'll compare and it will be false. Now tell me this. Will you continue going through all the other iterations?
No,
No,
sir.
no, sir.
No.
I was just saying the general case.
Okay, right. So you will not continue because you have encountered a return, right? So you will do 2 iterations. In fact, yeah, you'll do 1.5 kind of, right? So you will do 1 full iteration of the inner loop. But then on the second iteration, you will just terminate the entire procedure, right? Because 0, 0 and 0, 1, 1, 0 is not the same. Okay, so any questions regarding this adjacency matrix for directed and undirected graphs? Okay, I'll take it as no. So now again, this is an example of undirected graph. So it will return true. Now, how many iterations will we go through before we return the answer?
In this case,
We'll have
each
to
case
go
has
to
to
each
be.
case, sir.
Yes, sir, each case has to be
9,
tallied with
right?
each case.
Yeah.
So since 9, so 3 iterations.
Yeah, so 3
Three of
iterations.
3 of outer and 3 of inner.
Right. So 3 in the outer and 3 in the inner. Now, just an extension to this. Now, do we always have to do 9 iterations, or is there an easier way to write this piece of code?
It's an exit loop.
Okay, but we are returning, right? So we are returning false. I mean, when you return for a directed graph, you will finish it sooner. You will finish it sooner than this, right? But are we doing any wasteful computation here? Are we doing anything extra? Can you do it less than?
Sir, since
We can
it
keep
is a
visited, sir.
since it's a symmetric matrix like 3 cross 3, so we can take the for each seed. So we can just say RR or something like that. But that won't work. That won't work.
Sir, we are
If we check RC not equal to CR, then we don't need to check again for CR not equal to RC.
Okay, that's correct. Now let's
Yes, sir. Diagonal elements, we can just avoid checking them.
So we only have to go through the upper triangle method.
that's the point, right? That's the catch, right? Yeah, that's the keyword I was looking for. Let me now share the screen so that we can quickly write down that part of the code. Now, so the code is what? The code is procedure is undirected, right? Step one is undirected. Right, you have a graph and then okay, so this is what we wanted to do, right? Now for each R in rows of graph, I still do this, but let's see where to cut it off. For each C in columns of graph,
If C is greater than R,
okay, if C is greater than R,
check for RC, CR not equal to RC, then return false.
okay, not equal to graph RC. Okay, you're returning false, and okay, so we have otherwise you return true, right? Let's just quickly go over this. Now, for so you go through each row, you fix a row, and then C is initially 0 to start with, right? So the moment C becomes, so do you even need to check for C equal to R?
No, sir.
not equal to R.
No,
It will never have edge to itself.
Okay, so is it okay if we replace this? Okay, you are anyway.
Yes.
if C is equal to R, then it will also check diagonal elements.
Okay, so you are doing the lower triangle. Which part you are doing? I
Lower triangle, sir.
Okay,
Lower
okay.
triangle.
Okay, so you are checking the elements which are above the main diagonal, right? Here.
Yeah.
Okay, yeah. So
Sir, we have to check both upper and lower triangle.
Either. Not
one of these two,
both.
right? We don't need both. So if C is greater than R, until C less than or equal to R, we are ignoring, and then moment C becomes greater than R, we are checking, right? And this will automatically ensure that whatever you need is captured.
Yes, sir.
Okay. So let me go back to the screen. Okay, so that's directed versus undirected, right? So here you will have to go over all these things, right? So, and mainly you have to check for off diagonal elements, right? Anyway, diagonal elements are going to be 0. And here all of them match, therefore it's undirected. Okay, so that's done. Now let's look at this problem where you count the total number of edges in a graph. Okay, let's call this procedure edge count. Edge count is equal to 0, and at the end I'll return edge count. Now, what happens in between?
For each
We can iterate through rows and columns.
R in rows, and for each C in columns.
We iterate through rows and columns and see if there is any edge. I mean, if there is one.
If RC equal to 1,
If
then
graph
edge count
of
equal to
IJ
edge count
equals
plus
to
1.
1, edge count plus.
Okay, right. So
Edge count plus 1, yeah.
that's correct. So we just iterate through the rows and columns, and if you end up seeing an edge between a particular R and a particular C, then you do edge, okay, and then you return edge count. Is that correct?
Yes, sir.
Okay. So we have added some space in between. Can you think of any reason why there is a space here? Is this always correct?
Some code should be filled in it.
Correct. So what code is it? Why is there a space?
Because a single edge is counting twice.
Good point. So when will that happen? When will a single edge be counted twice?
In undirected graph.
Okay. So what do we have to check here?
If there is an edge from 0 to 1 and 1 to 0, then we will count only
If
once.
the graph is
Correct. But
the
we have
graph
just
is
done something.
undirected, we have to divide by 2.
That's correct, right? So we have to check if the graph is undirected. So can I use what we did before? We wrote a procedure before this, right?
Yes, sir. Yes, sir. Yeah. Yes.
So we can reuse that. So if you have to reuse that, what will be the pseudocode for that part which sits here? If is undirected of graph, then what should I do?
If RC equal to 1 and CR equal to 1, then H count equal to H count divided by 2.
Correct, right? So that's what we do. So if it is undirected and if I find that my existing graph is undirected, then I just divide my H count by 2, right? I can either return H count by 2, but I don't want to return twice. I don't want two return statements unnecessarily. So I'll just divide H count by 2 and finally I'll return the H count. Okay, so if the graph is directed, then this will be false. So I'll just return the H count. Okay, did everyone get this part? What we did here?
Yes, sir.
Yes, sir.
Okay, so we have to account for the specific case of graph being directed or undirected. Okay, so that is one thing. Now we have one more property of a graph, right? So a clique. I hope you all know what a clique is.
So a group where every member is connected to every member.
Yes,
Correct,
sir.
right? So every node is connected to every other node. So I want to write a procedure where we check if this list of nodes, right? C is a list of nodes. If C forms a clique in that particular graph, so that C is obviously a subgraph, right, of graph. So that set of nodes is going to be a subgraph of this bigger graph. We want to find if that forms a clique. Okay, so can you write a procedure for this? How will you go about it?
For each I in for each row R in rows of graph, for each columns and in for
So
that
C is a
row.
list, right? C is a list, right?
Yeah, C is a list of nodes.
Yeah, that would be then first. I mean, we have to iterate through the list actually. So
Okay, yeah, give me the overall idea. So you'll have to iterate through the list and then do what?
and see if there is a what is it? The link between those two.
We will check for each row and each column in that row. If there is an edge for that column, we will check for that column's row. That if another column has row the edge to that, and we will check whether that column has for that row, whether the first node has column with that row.
Or we can iterate through the elements of the C list and we can check if every other element is connected with.
Okay, let's see if that will work.
I equal to J, sorry. Except for the self node, we have to check for all other if it's equal to 1.
Okay, except for the self node, yeah, except for the self loop, right? So there should be no, of course, you don't want self loops, right? So you're not interested in self loops. So we'll iterate through C, right? Because that's kind of easier in this case. So for each element in C, for each node that is there in C, because ultimately we are only interested in the subgraph, right? Not in the entire graph. And for each C in C, right? What are we going to do? We are going to ask what if condition.
If there is an edge between R and C.
Correct. There is an edge between R and C, but not just that, right? So we don't want to compare.
Yeah.
Same columns 0, 0.
Okay, so what will this? I've done something different here. So I am asking if R is not equal to C and if there is no edge between R and C, what should I do?
Return
False.
False.
Return false.
Okay, that's correct. So if there is no edge between R and C, you return false. Otherwise,
then it will return true.
right, all the way at the end, right? So this is an interesting way to write a code. I mean, not in, where you could think about it as interesting or not. That's up to you. But when you want to see if a property exists for some collection of items, right? Now you could either approach it. You could approach it in two ways. You could either ask here every pair of elements should satisfy the property, right? You could look at it that way. So if you had to modify the code in that way, then for a clique, how many pairs of nodes should you consider?
More than 2.
So 3. If there are n nodes, right? If a clique of size n you have to detect, how many pairs of edges should you check?
At least
Minus
three. At least 3.
In general, n, right? If you have n nodes, a clique of size n.
Yeah.
We have to check
size n.
From n choose 2, right? So you will essentially have to check n choose 2. Every pair of nodes you'll have to check, right? So one way to do that is you could add up all these things. Whenever you see that there is an edge between a node, a pair of nodes, you keep adding them. So for a clique, what will be the sum of the edges that are formed?
Like here we have a clique 103, then there should
n choose 2, right? So n choose 2 edges will be there. So you could do it mathematically and compare the number of edges formed and see if it is n choose 2. Here it's 3, right? 0 for 0, 1, 3, there are 3 edges, right? 3 choose 2. Now you could do that. The more programmatic way to do that will be what? You check every pair of edges. The moment you find a pair of edges, a pair of nodes which do not have an edge, then you return false, right? So you see the first instance when the property will break down. So whenever the property breaks down, you return false. Okay, is that idea clear?
Yes, sir.
Right. So
So the smallest clique can have how many members?
Okay. This is a slightly tricky question because we could, I believe, define a clique of, I don't know if you can define a clique of size 1, right? So if you have a graph of size 1, then every node is connected to each other node, right? It's like a vacuously true statement. And then such statements are called vacuously true, where you can check that out. So you could, in principle, say that a node of a single node graph, right? Every node is a clique in itself, but they are not very useful or interesting. So you must have at least 3 nodes for a clique to be non-trivial and interesting.
So we can check all clique also by in degree or out degree, na? Because 103 is a clique and 1 is giving 2 in degree or out degree, which connects 0 and 3. Same as 0 passing 2 in degree out degree.
Okay, for here, so in this case, degree is slightly, it's like you have only one degree, right?
Will we consider in degree and out degree in the case of undirected graphs as well?
No, we won't, right? So here, that's what we have, only a degree. We don't have an in degree and out degree, right?
Yeah.
Okay, sir.
Right.
On undirected graph, you only have in degree and out degree.
Right. So can we move on to the next one?
Yes, sir.
Okay, so again, this is this clique of graph 0, 1, 3 that will return true, right? So basically, you have to look at these elements 1, 0, 0, 1, 0, 1, 0, 3, and then 3, 0, 3, 1, right? So you have to look at these things, and yeah. So someone has raised their hands. Can you please unmute?
Sir, we can say clique is cycle.
Well, there is obviously going to be a cycle in a clique, right? So if you have a clique, then there will be several cycles, right? So because it's a complete graph, right? So it's a complete graph. The clique portion is complete, so you can always cycle back. But if there is a cycle, will it become a clique? No, right? Because you could have a cycle and still that may not form a clique. Correct?
Undirected, I think it will form a clique, right?
Not necessarily, right?
If you have a if you have a cycle
Sir,
of
why,
5
sir, if
elements,
there is a cycle, why it is not a clique, sir? There is, if in a cycle, every other member is connected to each other, right?
No, we are looking at a particular example, right? Look at a bigger graph, and then you will realize that even if a cycle is there, that need not be a clique, right? You don't need to.
for a cycle of 5 elements, you only need 5 edges. But for a clique of 5 elements, you will need 8 edges for that to form a clique.
Okay, does that convince you? So
Actually, clique is a part of incomplete graph which is complete always. This is a definition of clique.
So a clique is a part, not so the clique is complete in itself, but it can be a subgraph of some other bigger graph, right? So that bigger graph need not be complete, right? Yes. Anyway, so I think we are like moving too much out of the CT landscape. So for CT purposes, this is the clique, right? So I hope that part is clear, right? So maybe we'll move this discussion to the end. Is that
Sir,
fine?
I have a question, sir.
If it is CT related, we can go ahead.
Yes, sir.
Yeah.
In a clique, does it have to be like each node has to be connected directly to the each other, or like in a 2-step or 3-step is okay?
Yes, right. So no, directly it has to be connected, right? So it's not.
So the picture in the it is right now. It's visible right now. It is not a clique, right?
The entire graph is not a clique. So 0, 1, 3 is only a clique, right? We are only asking if a subset of nodes is a clique.
Okay, sir. Okay, sir. Okay.
Right. Yeah. So I'll move on. So the next one is to see if we have a path from one node to another node, right? So think about this directed graph, and you are having this procedure, right? Is there a path from one node to the other? So P is what? P is going to be a list of nodes, right? I'm going to give you a list of nodes, say 0, 1, 3, and you have to tell me how to find out if there is a path from the or if P makes a path in this graph, right? So I'll put it that way. So let's say P is A comma B comma C. You should tell me if A, B, C forms a path in this graph.
For each
Yeah, I mean, you just give me the overall idea, right? So even before going to the pseudo code,
we will check for each node, sir, whether it is connected to another node, and for that another node we will check whether it's connected to some other node, and that's.
And that third node is connected to the first one.
Okay. All right. So that's one answer I have. Anyone else wants to comment on how to find?
Can we not do it the other way? Like, hello.
Yeah.
Can we not do it the other way? Like, we can just check if there is no any path. I mean, there is no. Hello.
Yeah.
Yeah. If there is no link between two, we can just say there is no connection.
Okay, that is one thing. And then how will you find if there is a connection overall?
Else loop, we can also provide an else loop for that.
Okay, any other ideas? Anyone how to find a path?
Your DFS is.
Okay, DFS. Okay.
Can we go like in each rows? Like if we take the 0, 0, if the entire column of 0 is 0, 0, then there is no path at all to that 0.
Okay.
Is that the correct way?
Well, here at least you seem to have at least one edge, right? Somewhere.
Yes, sir.
Okay,
so there is a path like for every.
Right, some path is there. So only the question is whether the list of nodes given in P form a path, right? So that's the catch. So let's try to break the problem down into two parts, right? Can someone tell me how you will break it down into a simpler problem or which you can solve? If I give you this thing that you can break it into smaller problem, can you think of a way to do it?
So is it using recursion?
Yes, yeah, exactly. Can you think of a recursive solution to this?
If we can determine the node is connected to a corresponding adjacent node,
We just start from one node, then we move to the another node, and from there we another again call the recursion.
Okay, yeah, correct. Good. So now, which node will you start off with?
0, sir.
Okay.
Any node.
How will you know?
no,
that-
I think we can start off with almost any node. There is no
Yeah.
root node per se here. We can just start off with
Until and unless we provide
yeah,
that.
and it will form a cycle. Those are all directed edges.
Okay,
Right.
so let's start with that idea. It's a recursive code that we're going to write. So I am giving you N1 and N2, right? This is a specific code that I came up with. So your code could be different, but assuming that this is what we start with, and you have to figure out what N1 and N2 could be, what will be the RHS? What options do you think are appropriate? What can I fill N1 with? What is N2? P is a list, right? So P is a list.
First of P and first of rest of P.
Very good, right? That's correct. What will be the next step?
If we will check whether we have a node connected to this, that means
Edge connected them.
yeah, edge connected to this. That
Yeah,
graph N1 N2 equal to 1 or not.
Okay, if there is such an edge, what will you do?
We will check for we will update the N1 and N2 in that case. N2 for N1 will become our the first of rest of P, and we will take the
We can
rest.
call
okay,
the
I got it.
procedure. We can call the procedure
rest
again
of it,
with the rest of.
Okay, right. So
rest of N2.
correct. So let's go ahead and do that. So again, this is the same philosophy, right? So if the condition breaks, right? If whatever condition you want to check for, if it breaks, return false, right? That's the simplest thing to do. So if there is no edge from N1 to N2, then there is no path, right? So first two nodes itself are going to fail you, and you can return false right away. If not, right? So you can go over the first node because you know that you can go from N1 to N2, right? So you have made one step at a time, right? All journey starts with the first step, right? As they say. So you have made the transition from N1 to N2. Now you are standing at N2. You don't need N1 any longer. So you call is path from graph on rest of P. Correct? So the recursive part is clear, I hope, to all of you. If not, please stop me. Now, when will this terminate?
When the length is equal to 1 or less than 1. It will return that list.
So what will it return then?
It will return the list.
Okay, will it return the list?
No. It will return true. True. It will return true.
Correct, right? So if length of P is less than or equal to 1, you have basically reached the last node in your path, right? So you have finished the journey, so you can confidently return true. Okay, so if you look at this is path of graph of 132, let's just execute it. So what will be how will this recursion unroll?
So first of all, we will check whether the length is equal to 1 or less than 1. So it's not, so we will never go to the if loop. Then N1 will be assigned to the first of this list, that is 1. N2 will be assigned to the first of rest of this list, that is 3. We will check whether a graph 1, 3 is equal to 0. If it is 0, then we will return false. If it's not 0, that is 1, then we will call is path for rest of P, that is 3, 2. We will call for 3, 2. Then we will check for 3, 2.
So this will unroll as is path of graph of 3, 2. Right now, what will be the next recursive call?
Graph of 2.
Okay, and now it will return.
It will return true.
Okay, did everyone get this part? Is there any question that you would like to ask at this stage?
No, sir.
So this procedure is clear to me, but can we do in such a way as well? Like if we check the in degree of 0, if for every row, if it is after checking for every row, if all the rows are 0, then there is no path to that 0. So
there
we
is
can
no
return.
path to 0.
Let's
There is no edge.
there is no edge. So let's say for in this code, like if 0 to 2, if there is 0, so in such case there is no path to 0. Can we conclude in such a way, or that is wrong?
So that might help you, but even in this case, it will fail, right? There is at least there's no row which has, or there's no row or column which has all zeros, right?
Because it is connected actually.
It's not strongly connected. So see, this is a directed graph, right? So in fact, if I were to give you 0, 3, right? 0, 3 as the list P, how will you proceed? Right? 0, 3. There is no path, right? Of course, there is a path via 1, but then the condition is 0, 3 itself is not a path, right?
0, 3 is not a path.
Right. So the question actually is, I'll make this more precise. So P is the entire list of nodes on the path from the first node to the last node in P. Right. So we are not just asking if there is a path from the first node of P to the last node of P.
No,
right. That's the question.
Okay. No, that I got, sir. But what I'm just saying is, if there is an entire row or entire column that is 0, then it is not. Then there is a not path to every other node. That is what I'm saying.
So let's take 0, right? So if there's all the elements in this row are 0, then there is no outgoing edge from 0, right? But there could still be an incoming edge. So 0 could still be on the path.
Yes, sir.
Okay. Okay.
Right. So for example, just delete this 0, 1, right? This is the appending element, right? Just delete this, make this 0. So you could still have a path that is 3 to 0. Right? I can go from 3 to 2 to 0, but I can't have any path that goes out from 0.
It is just like mentor case. 0 can't mentor anyone, but it can be mentored by someone.
No, but it won't be a connected graph then.
See, even this graph is not connected, right?
No, sir. In such case, let's say there is no path available. I mean, let's say the entire column for 0. I mean, there is no path from, let's say 1 is not connected to 0, 2 is not connected to 0, 3 is not connected to 0. So it says 0 is not also connected to 0. Let's say 0 is an abstract node somewhere. So it's not a connected graph actually.
Correct.
So in such case, that would be true, right?
No, I said for column, sir. I'm not saying for row. If the column of 0 is entirely 0, then.
So let's take that also, right? Let's say the column of 0 is entirely 0, which means there is no incoming edge to 0, right? So let's cut off 2 to 0.
There is no outgoing edge to 0.
There is no incoming edge, right? If you cut off
column shows
so if you
incoming
make a column 0, then there is no incoming edge to 0, but there could still be a path from starting from 0 going to 2, right? So for example, 0, 1, 3, 2 will still be a path. So if the entire column is 0, it's still hard to determine whether P is, you can't rule out the fact that P is a path.
Okay, if we go by my approach, then we have to check for the row and the column of 0 as well. They simultaneously have to be 0.
Yeah, in that case, as someone mentioned, right? It will be an isolated node.
Yes, sir. Yeah, like an abstract node, like it's not connected to the main graph actually. So in that case, that would be true.
That is correct, right? Yeah, that I agree. Yeah, correct. If you have such a node, then if that node happens to be in P, then it's hopeless, right? It can certainly not be a path. P cannot be a path.
Yes.
Okay, so any other questions? Shall we move on?
No questions, sir.
Okay, so this is an extension of the previous problem. So you are just asking if you have a cycle, right? So I am giving you this list of nodes again where the list of nodes C, right? That should form a cycle. So how do you do this?
We will check
We
that
will check
from
for each column, for each row each column in that row if it has an edge, and if it has an edge, we will check for that columns of that column,
yes.
whether it has some edge or not. And similarly, we will move on till we find an edge from the last node to the first node.
So the main idea of cycle is from where we are starting, we can move back to that starting point.
Okay.
Or sir, we can go as such as well. Like we can we will check for C cell is for, so all the element we can check for the procedure we have written for the click.
Okay.
If that returns true, we can for, and if that returns false, we can reduce the element of the C. We can reduce one, and then again we will check for the click. So
okay, you mean click or the path?
path.
Click has to be fully connected. I mean, complete graph, right?
Sir, yeah, like we can we have to choose for path.
The path graph.
Okay, so how will you use the path procedure here and make this code like really short? So if a cycle has to be there, then it should be something first. What should it be in the first place?
And call recursively that path.
Okay, so see, if something has to be a cycle, then it has to be what first? It has to be a path, right?
Should be there.
It has to be path, the starting node and the end node.
Correct. The starting node and the end node should be the same.
So
it should be the same, right?
First of C and the last of C should
exactly.
be connected.
Right. So if it is not a path, okay, if the C is not even a path, then
return false.
Hopeless, right? So you return false. If it is a path, then what do you do?
Return true.
Do you return true, or so what if it is 0, 1, 3? It's a path, right?
Yeah.
So you will end up
we will check for first in that element whether it has an edge.
Okay, so see, maybe here I didn't specify one thing. So when I say P is a cycle, I'll make sure that the first node and the last node are I go back to the same, right? So that full path is the cycle, right? So I won't leave I'll complete the cycle rather. Do you get it? So for example, I'll ask the question, is cycle of graph comma 0, 1, 3, 2, 0. I won't stop it at 2. I'll go back to 0.
Yes, so we have to come back from where we start.
Okay, so what is the final condition here which will make this procedure complete?
First of C and last of C are connected.
Okay. In a single statement, can you tell me what it will be? It's a single statement. Is this correct?
Yes, sir.
Yes.
First element and last element should be the same.
Right. So let's just look at this example. Right. So 0, 1, 3, 2, 0 is a cycle. How do you check that? First of all, is it a path? 0, 1, 3, 2, 0 is a path. And then you check if the first element and first node in the path is the same as the last node in the path, right? In that case, you have a cycle, of course. So we are not talking about the case where you have a bigger cycle and then some smaller cycle is hidden somewhere. All that is like too complicated, right? So you're just asking if this particular path is a cycle. Okay, is this code clear to everyone? What we have done?
Yes, sir.
Yes, sir.
Okay, so is this?
So we are just appending the list when we are checking for the cycle. Actually,
we are
by the first element twice. I mean, you're adding the first element 0 at the last element.
Exactly.
Cycle, and the rest thing is completely same.
Yeah. Okay, so this is not a cycle. 0, 1, 3, 0 is not a cycle because it's not even a path, right? So it's not even a path. Okay, so this is the first set of slides. I'll now share the second set of slides, which are more closer to what you have seen in the assignments, I hope. Okay, can you see the second deck?
Yes, sir.
So this screen is visible.
So I have a question. Last slide,
Yeah.
we have 0, 1, 2 was missing, right? 0, 1, 2, 3.
Yeah, so that will
one node
return
was
false.
one node was missing from the part.
Yeah, that's why it will return false, right? That's an example for not a cycle, something not being a cycle.
Okay.
Right? 0, 1, 3, 0 is not even a path. Therefore, you won't even go to the case where it becomes a cycle.
Okay, sir.
Okay, so this is a question, right? So you have to create a graph. You have the words data set, and the nodes are going to be the words, and you'll have an edge between nodes, between a pair of nodes, if both of them start with the same letter. Okay, so assume that you are given a procedure, you don't need to write this procedure. Starts with is a procedure that will return the first letter of the word. Okay, so this is given to you. Okay, with this information, you have to create a graph. So how will you go about it?
So we will explore the words and we will check whether the first of that list that is returned matches the first of the list of another word.
Okay, right. So that's the idea. Now let's go step by step. We'll first get hold of all the words in the data set in a dictionary, right? So
Yes.
what can this dictionary have? What can it have as the keys?
Indexes as keys and words explode words as values.
Okay, right. The words as the values, right? So now you initialize an empty dictionary and then you say, while table 1 has more rows, you read the first row in table 1, and then before moving the card to the or row to the table 2, what statement should you add?
If words I so just words I the first of words I equal to first of words J.
Yeah, I mean that's going a bit too far from the stage, right? So now we are just getting hold of all the words. We are just getting the words of the data set into a dictionary.
Okay.
So what will be the statement here?
For words I equal to explode x dot word equal to explode x dot word.
Okay. Anyone else wants to try?
Word I is the value I if the is equal to
So
another.
we could use the words x dot sequence number and then explode x dot word to save those in the list form for that particular sequence number of that card.
Okay. So yeah, right. So let's do that. So this is what we are doing, right? Words of x dot row number is x dot word, right? So what do we need? We need nodes which are indexed by row number, right? So we need the row number. So x dot row number, and you need to store the word corresponding to it.
So since we are going to check for the words with the same starting letter, can't we just concise it
Correct.
and just say that explode the word at the same time and store it as value?
We can just store the first letter. That will work. What is this? What else are you saying?
I'm just saying that for that particular index, just take the first of explode of word. Explode of word will return me the list of the letters of that word, and I will just take the first of that and store it as value for that particular index.
Yeah, fair enough, right? So I have used this as starts with, right? So I'm saying that there is a procedure called starts with.
Okay.
To return the first letter of the word, you could have as well written it as starts with of x dot word, right? So that also makes sense, right? It's just a different way of doing it, right? So you could do that also. Now you return the words, right? So you have a dictionary of words indexed by the sequence number, right? So let's say it's a very simple data set. It need not be the same data set, right? So some very simplistic data set. 0 is 1, 0 is good, 1 is great, 2 is fine, 3 is 4, right? Now let's come to the main procedure where we have to create a graph. Okay, so is this fine? We have, right? How big a graph will this be?
This
4
will be a
cross
3
4.
by 3, 4 by 4.
4 cross 4.
Correct,
Five.
right?
4 cross
4 cross 4, right? So it'll have 4 because there are like 4 words and keys of words will be what? 0, 1, 2, 3 in some order, right? It will be a list in some order, and then your length of that will be 4, right? So it'll be a 4 cross 4. We have created the graph. Now, what will be the next step that we do? We'll iterate through the graph, right? For each R in rows of graph, or each C in columns of graph, we have to create an edge. When do we create an edge?
If the first, so we'll have to explode the word, sir, and we will check for if the first element of that list is equal to the first element of the other words list.
So in this case, it's a simpler thing, right? So we can just use this procedure that is given. So we can just say,
okay.
Right? So we can just say, if words of R starts with this letter and words of C starts with this letter, right? So now, because of this, what we are going to do is, if R is not equal to C and if the first letters are the same, just add an edge between R and C. Okay, so what kind of a graph will this be? Will this be directed or undirected?
Undirected.
Undirected.
Right, so it will be undirected. Right, so it will be undirected, and finally you return the graph, right? So these are two procedures. You are not done with just writing the two procedures. You have to call them appropriately, right? So you first get words and store it in a dictionary called words, and then you pass words into create graph. Okay, so graph will finally be this object, and this will look like this, right? So it will be a 0, 1, 2, 3. 0 is connected to 1, 1 is connected to 0, 2 is connected to 3, 3 is connected to 2, right? So 0, 1, 2, 3. Okay, so it's a disconnected graph with two components, right? 0, 1 forms a component, 2, 3 forms a component, right? So are there any questions in the code that we have written so far?
No, sir.
Okay, so
no, sir.
Simple enough. Now let's look at the number of unique starting letters in the data set. Okay, so for example, in this data set, how many unique starting letters are there? 2, right? So it's very easy to find it using words itself, right? You don't need the graph, or you can just iterate through the keys of word, the values of words. Every time you encounter a new word which starts with a new letter, you just keep a count, right? So you can do that. It's a very simple way of doing it, but let's make it slightly complicated and try to do it using the graph, right? Assume that the graph is given to you and you need to find out the unique letters, right? Unique starting letters, right? How many unique starting letters are there using the graph? So what basic idea of the graph will we use here?
It is a symmetric graph, so
number of subnets.
Sorry, can you come again?
Number of subsets or subnet, whatever.
Correct, right? Number of subnetworks, or if you want to use a more technical term, it's called a component, right? So this is a connected component, as we call it. So 0, 1 is connected. I mean, every node if you look at a particular letter and look at all the nodes that share the same letter, they'll all be connected. Do you agree?
Yes, sir.
So all the words that start with a particular letter will be connected.
Yes, sir.
Likewise, all the words that start with a different letter will also be connected.
Yes, sir.
But these two connected parts, right, they won't share any edges. Do you agree? So for example, 0 and 1 share an edge because they start with the same letter. 2 and 3 share an edge, but 2 and 0 do not have an edge because they don't start with the same letter, right? So what we can do now is we can explore the graph, right? We can explore the graph starting at any node. So what is the method that you know to explore a graph?
For each row and column.
So what is the principle, like the basic idea that we have studied in these weeks? DFS, right? So we start
DFS.
on one of these nodes, right? Let's first look at DFS. So let's just revise this DFS a bit. So what do? You have a graph which you want to do DFS on. You start with a node. Okay, visited is a dictionary. You keep track of which nodes were visited. So if you are starting from node 0, you say visited of 0 is true, right? So you have visited 0, and then you go through each C in the columns of graph, right? And if there is an edge from node to C,
DFS for that column. And if it's not visited already.
Right. And if it's not already visited, you go ahead and visit. Okay, visit of graph, comma, C. Okay, this will do your DFS. Now, the catch is this, right? So I'll come back to this. Don't worry about this now. I'll come back to this. Here is a bigger piece of code, right? This is the main piece of code that will help us find the number of unique letters. Okay, so COM stands for community, right? Com stands for community. How many communities are there? Here we have 2 communities, which is what we have to find. Now, for each node in the graph, for every single node in the graph, you have to run DFS. Okay, you'll have to run DFS from every node. But if the node is already visited using DFS of a particular node, you don't do DFS on it. Right? So, for example, let's say you start DFS on 0. Now, what all nodes will be visited from a DFS of 0?
0 and 1.
0 and 1, right? So, next time when you come across node 1, you check if 1
is already visited.
Yeah, you check if it is already visited. Now, if it is visited, then which is what we are doing here, right? If this node 1 is a part of a list called unique, if it is a part of the list, then don't visit. If it is not there, right? For example, node 2 will not be a part of the nodes that you visit when you do a DFS of 0, right? So when you come across node 2, then you start a DFS from that again. Okay, so every time you create a new DFS or every time you initiate a new DFS, you will be updating com to 1 by 1, right? So you'll end up with the total number of unique letters in the data set. Okay, so is this idea clear to everyone? Is there anyone who's having a problem with this?
Sir, can you explain it once again, please?
Okay, so the DFS part is clear, right? This is the DFS code.
Yes, sir.
Okay, so see, okay, let me come to this. Anyway, understanding this code is also useful for the exam, right? So let's understand this code. Can someone tell me S1 and S2 are lists? Okay, they are lists. Can someone tell me what this code is doing? Update of S1, S2. What is it doing?
If the element
it's adding
S is not in S1, then we will add it.
Those elements which are not in S1.
But there are in S2, it will add those to S1.
Yes, sir.
Okay, so what you trying? Yeah, that's good, right? It's actually a set. I'm trying to make it a set here, right? That's a very good observation. So assume that S1 to begin with is having unique elements, right? 0, 1, 0, 1, 2, right? Now, if S2 is also 0, 1, 2, what will happen to S1? I mean, what will happen to update of S1, S2? It will not disturb S1, right? Okay, so let me just take this procedure alone and show it to you. It's important to understand this procedure. So let me share the screen instead. Okay, so are you able to see the screen now? I changed it.
Yes, sir.
Okay, so let's try to understand this procedure. So I'm saying that S1 is what? Let's say S1 is 1, 2, 3, and S2 is say 1, 3, 4, 5. So what will be update of S1, S2?
1, 2, 4, 1, 2, 3, 4, 5.
Yes, 1, 2, 3, 4, 5.
Okay, so does everyone agree with this? Is there anyone who is not agreeing with this or who has a doubt here? Please stop me now. Okay, so you're all clear, right? So what we are doing is we are checking if S2, every member is there in S1 or not. If it is already there, then you don't do anything. If it is not there, then only then you're adding it to S1.
Also, we will maintain the order.
Yeah, the order is also maintained.
Yeah.
Okay, so this is what update of S1, S2 is doing. Now, let me bring
So
in
it's
this.
basically S1 union S2, right?
Yeah, exactly. It's S1 union S2. Correct. Right? It's the union. So that's what one of them mentioned. It was a set, right? So it's doing the union operation on the set S1. Now, this is the code that I had, right? So visit is a DFS, right? Visit does DFS of that particular graph. Now, you focus on keys of visited. So keys of visited will be what?
That particular clicks, that particular cycle that have the first letter as same first letter. Those nodes.
Right. So let me maybe quickly draw a graph, a small enough graph that will help us understand this better. So say this is 1 and 0 is 2, right? So 0, 1, 2. Okay, so interestingly, these subgraphs will be what in this case? Each subgraph, can you tell me what kind of a graph it will be? They'll all be cliques, right?
Yeah, they'll all form cliques.
Okay, they'll all form cliques. Now, of course, they'll be undirected. So let's go ahead and remove the direction. Now, let's connect them. Okay, so these are connected. Okay, so now this particular clique could correspond to the letter, say, E, and this particular clique could correspond to the letter F.
Sir, a small doubt regarding DFS, a general doubt, not related to this. Can we say that recursion is more efficient than iteration?
I'm not very sure about that. That we'll have to look at. I think the language to some extent
Because
matters.
it was a question in a particular activity in week 12.
Okay, so I don't think with the CT that we have studied, we can answer that question, right? So the efficiency, I don't think we can answer that with the CT knowledge that we have. We might have to go beyond CT and look at how recursive calls are managed by the system and how iteration is managed by the system, right? So all that we need little more knowledge. At least I am not in a position to answer. Okay, so let's look at this, right? If you do for each node in rows of graph, right? We'll start from 0. So I'll call, is 0 a member of unique at this stage? Unique is empty, right?
No,
so
sir, it's empty.
Right, so I do DFS on graph, 0, this empty dictionary, and I get visited. So what will be the keys of visited? When I do DFS on 0, what will be the keys of visited? After doing DFS on node
0, 1, 2, 0, 1, 2.
The nodes.
Right, this will be the keys of visited. Now I'm saying, and this is what I'm saying, right? Now I'm saying unique is update of unique, keys of visited. So what will be unique? No?
The unique nodes. No?
It will be the union, right? As we just saw. Unique will be 0, 1, 2 now. So it's empty list union 0, 1, 2. Correct? So unique will be 0, 1, 2. Now com will be incremented to 1, right? So com will become 1. So you have found out one community. Okay, now you'll go back, you will go to the second node. So node will become 1. So is 1 a member of unique?
Yes.
Right? So you won't enter this.
Yeah.
Now you'll go back
Similarly
to
for 2 also.
right? So you won't enter this. So for every node that forms a part of this DFS tree, you will not enter. Now you'll go to 3. Is 3 there in unique?
No, sir.
Right? So you'll do DFS, and then on 3, if you do DFS, what will be keys of
3, 4,
visitor?
5. 3, 4, 5.
Right? So this will be keys of, then you will do unique of update of unique
0, 1, 2, 3, 4, 5.
Right? So yeah, this will give you the whole thing. Okay, now com will become 2. So you have found out the second community. Now we'll go back, and if you do it for 4 and 5, 4 and 5 will already be there in unique, so you will not do anything. Okay, so this is how you find the number of communities that are there in a graph. Okay, did everyone get this part? At least to some extent.
Understood, sir.
Okay.
Yes, sir.
Okay, so let's go back to this one. That's the end of this, right? So let's now look at another example. Now this is second situation. Okay, you have a family tree and people are nodes, and there is an edge from parent to child. Okay, now we have to find the list of descendants of a person. So, for example, 0 could be, let's say, mother, 1 could be father, and they both have a child 2. Okay, and then 2 gets married. So 2 could be, say, let's say a boy, 3 is a girl, right? So this is father, mother. They have 2 children, right? 4 and 5 are 2 children, and 4 is 5 sibling, and 4 gets married to 8, 5 gets married to 6, 8 and 4 give birth to 9, 5 and 6 give birth to 7, right? So you want to find the list of descendants of a person. So let's say we want to find out all the descendants of 1. So this is son or daughter, grandson, granddaughter, great grandson, great granddaughter. Okay, so that's you want to get the list of all these relations. How will you do this?
We can call DFS for 1 and then 2. Similarly for 4 and 9, and then again for 5 and 7.
You have to call DFS every time on each of these nodes.
I mean, if we call DFS for 1, it will automatically call itself recursively.
Correct. Right. So let's do that. I'll again sketch out give you the skeleton of the code, and then you can fill in the rest, right? So you have this procedure, descendants test graph comma p, right? P is the parent, P is one node. It could be, let's say, 1, right? P could be 1 here. Okay. So how do you proceed?
I think a base case could be if there is no in degree of any vertex, then
out degree. No, if there is no out degree, then it will
for every
just...
out degree we'll have to keep recursively calling and checking for its descendants.
Okay. All right. Now, what will be the recursive case?
It will check for say for one node and the another. If there is an edge, directed edge between those two, then it will call the DFS for the column part and the second node or the daughter node. It will call for that, and it will check for the edges for that.
Okay. Okay. So here's what we're going to do, right? So we're going to maintain a list L for the descendants, and we are going to look at each child of P, right? We are going to look at the children of P. Okay, so for each, I'm calling it index, right? For each in columns of graph. Now, if in happens to be a child of P, what should we do?
we will call for this for graph 2 for or that particular index.
So if ind is a speech child, right? So if ind is speech child, then we call
descent graph T.
Yeah.
So in the index.
Yeah, just give me 1 second. No, yeah, no, yeah. Sorry, yeah. So L is you first add it to the list of descendants, right? So your child is obviously going to be your first descendant, right? So you add the child to the list, and now you call descendants on
Recursion on
graph of
independent.
index.
right? So you are going to now find out all the descendants of your child and add it to the list.
Yes, sir.
Okay, is this clear to everyone? Is there anyone who is having a question here about how this works? Okay, I'm assuming there are no questions. So let's look.
Okay, sir, what? Yeah, shouldn't we give a base case? What if it's called on node 9? 9 has no descendants, right?
Good question. What will happen if it is called on node 9?
It will return 9.
Return empty list, right? So if it's called on node 9, there are will this if condition. See, that's a good question that you asked. See, base case is what here? Here, if the node is 9, will the recursive call even happen?
It won't happen.
Right? So it's you are saved there, right? So
A descendant for 9.
Sorry?
There won't be a descendant for 9.
Yeah.
There won't be any out degree for 9 basically. So
Exactly. So that kind of implicitly becomes the base case, right? You are implicitly checking for that. The moment you exit out of the loop and the moment you don't enter into any of the if conditions, right? You will be guaranteed to terminate without calling the function again. Okay, so let's execute this for this graph and see what happens. Now, when you call this on 1, graph comma 1, what will L in the first instance? What will L become?
L will become L plus 2.
L will become 2. You will just have the node 2, and then you will, once you add, call it again, right? You'll call descendants on graph comma 2. Now, what will L become?
4. 2 plus 2 and 4.
So it will become 2 comma 4. Right? It will become 2 comma 4. Yes, do DFS in the ascending order, right? So 2 comma 4, and then you will call the descendants of 4. What will be a descendants of 4?
2 comma 4 comma 9.
Right, and then 9, and then that 9 is kind of a base.
9 will return empty list.
Right, so L will remain.
Then we backtrack to 4 and to 2.
Now, where will we go back to?
First to 4, then to 2.
Yeah.
Then we will check for 2.
Then we'll go back to 2. Now, from 2, will we go back to 1 or
5? We will go to 5, call for 5. It will be 5.
Right, so 5 gets added as a descendant, and then you do descendants of 5, then
7
added. Now, descendants of graph comma 7 is again an empty list, so you go back to 5, you go
then 2, then
1, and then you just
it will return the list
of descendants.
Sir, how we are backtracking in this?
Here, right? So this is it's very similar to the usual DFS that we do, right? So when you call descendants of 1 in that first loop of 1, right? In the second iteration of the loop, you will come up, or rather the third, right? You will come across descendant of graph comma 2.
Yes, sir.
Right, so you'll do all that, and then you will go back to that again.
Oh, okay, sir.
Right.
Understood.
So, any other question about the descendants code that we wrote?
No, sir.
Okay, so I'll move on now. The same question, same kind of question, right? So same graph situation. You have to find the ancestors of a person, right? So you have to find the father, mother, the grandfather, grandmother, great grandfather, great grandmother. Right? You have to do all that. So let's say you have to do this for the node 7? How will you find this?
So we will just reverse the sequence. Earlier we will check in graph the index if there is an in degree. Now we'll check there is an in degree.
Right. So you will just do the reverse graph, right? You just reverse the graph. All relations get reversed, right? So instead of, so the relation is what? Father of or son or mother of becomes so child of, right? So that's the relation. So it gets reversed. So you have to reverse the graph. No
graph index p equal to 1. We will first append the index to L and then call for that for that index. It is for that index.
Right, but let's first do the graph, right? So let's.
So sir, 0 is a ancestor of 2, no?
Yeah, 0 is an ancestor of 2. Yeah.
So we need to look like out the edges.
We need to reverse. So the idea is
create a new matrix.
Yeah, every edge that is there like this, you just change its direction, and then you do DFS on 7. Right, so that part already. So you just reverse the edge, and then you find all the descendants of 7 in that reversed graph. Right, that's the same as finding the ancestors of 7 in the original graph.
We will just check for that in the original matrix if ij equal to 1. Then in the second matrix we will just assign ji to 1.
Correct. Yeah. So we'll do that. So you have length of keys of graph, and you are creating a new matrix, n by n matrix, right? And you are going through each row and column in reverse. Okay, you could also go through it in graph. It doesn't matter whether this is graph or reverse. It doesn't matter. If there is an edge from R to C, make an edge from C to R. Correct. So will this give us the reverse graph?
Yes.
Okay. Now, if you want to find out the ancestors of 7, you just do the following, right? So you reverse the graph and then do descendants on the reversed graph, comma P. Okay, does everyone understand this part?
Yes.
Any
Yes,
doubts?
sir.
Okay. Right, so let's just look at the descendants of the ancestors of 7. So if you work it out, I'm not working it out like the way I did it before, but you will end up with this, right? So first you will go to 5, okay, and then you will go to 2, then you will go to 0, and then you will backtrack. Then you will go to, then you will backtrack. You will go to 5, then you will go to 3, then you will backtrack. You will backtrack. You will go to 6. Right. So 5, 2, 0, 1, 3, 6. Did everyone get that? How you got the ancestors?
Yes, sir.
Yes, sir.
Okay.
Sir.
That is the second situation. Now we'll come to the third and perhaps the most complex situation that we have seen so far. So we have stations, right? Each node is a station. And there is an edge from station. There is a direct train connecting the two stations, right? So for example, S0 to S1, we have two trains, okay, T0 and T1 that ply between S0 and S1. And T0 runs in 2 hours. T1 takes 2.5 hours to reach, to cover the, not necessarily the same distance. The route could be different, right? But starting and end points are the same.
So in this matrix, the values are instead of 0, 1, they're a dictionary.
Yeah, we are going to do that. Yeah, we are going to have a dictionary, right? So this dictionary. Okay, so did everyone understand the graph here?
Sir.
Yeah.
Are we solving the questions for the end term exams in your practice session?
Yeah, this is some kind of a revision session.
Okay, sir. I was late, so I didn't.
Right.
It was happening. Okay, sir.
Yeah. Okay, right. So this is, so for example, in between S0 and S4, you have exactly one train, it takes 5 hours. Whereas if you could also go from S0 to S4 in, say 5.2 hours if you take T0, right? So T0, 2 hours to go to S1 and then 3 and 3.2 hours to go to S4, right? You could do that. Or you could just take a single train that takes you in 5 hours from S0 to S4. Okay, is everyone clear with the graph, the situation?
Yes, sir.
Okay, so now the question is, the first question, right? Determine if S2 is reachable from S0 by some train T. Right? So this is a particular instance of a general question. So you want to find out if a start station and end station are connected by some train T.
Yes, sir.
Okay, so that's the question. Now you have the adjacency matrix, and each entry of the adjacency matrix will be having the edge information, which is a dictionary, right? You have triple nesting, right? So you'll have dictionary of dictionary of dictionary.
Yes, sir.
Okay, that's the complexity. So this is the outline. Now you want to write this procedure. Is start station reachable from end station using this train? So for example, this could be S0, start could be S0, end could be S4, and train could be T8. Right? So that's the question. So how do you?
So we can go through each row and check if the value in that row and column, and in that keys of that dictionary that it stores as value, if that train is present or not. And if it is present, then we can check for that column and each column in that row of that column, and till we reach that end station.
Okay. Right. Anyone else? Does anyone else have any other idea?
Or we can call recursion procedure for this as well.
Okay. Okay, so let's go ahead and do this. So for each C in columns of graph, okay, for each C in the columns of graph, I'm going to see if the train is there
present in the dictionary or not.
Start to C, right? So start, let's say start is S0, right? So start C. So C can be
1 or 2.
Right? So let's say C is S1. So we are looking at graph of S0 S1. Okay, graph of S0 S1 is a dictionary, right? It's this dictionary.
Yes.
Let's say train is T0. So we're asking the question, is T0 present in the keys of this dictionary? That's what we're asking, right? Now, if this train is present in this dictionary,
we will call for this that column.
okay, does that make sense? What we have done?
Yes, sir. We will call the procedure for that particular column if that key is present or there or not.
Okay. Does this make sense?
So in this, sir, suppose if our start station is S0 and our end station is S2, we will check for each column of S0 if in that particular value that train is present or not, if that particular dictionary that train is present or not. If that train is present, then we call the procedure for that particular column, and we will check for that particular column if train is present in somewhere in values of that column.
Right. Yeah. So others, did others get what we have done here? Did everyone get what is happening here?
No, sir.
Okay. So tell me which part is not clear. So are you able to understand what this graph looks like? The dictionary of dictionary of dictionary.
Yes, sir.
Okay, so see, you want to find, the problem statement is clear, right? You want to see if there is this train, right? This train is, let's say, T0. You want to see if T0 starts from the start station and goes till end station. Okay, so for example, let's say S0 is start, like start and end are stations. Okay,
Yes.
train is T0. So let's fix at T0 and ask the question, from S0 to S4, do I know if T0 runs or not?
Yes.
Okay, that's the question we want to ask. Is the end station reachable from the start station using this train T0? So if I get on to T0 at station S0, will I eventually be able to arrive at S4? That's the question we want to answer. Now, for that to happen, this train should first of all be there in all the outgoing edges of S0. Do you see that? So the train should first of all leave from station S0.
Yes, sir.
Right. So for example, T7, if you replace train with T7, then it will fail, right? So T7 is not there in any of the edges that go out from S0. So the first thing that we do is, for each columns of graph, right? For all possible stations connecting, going out from S0, you ask this question: is train
T0 is present.
Yeah, is this train even starting from the station? So if train is starting from the station, so if train is a key of graph of start comma C, then it means that this train leaves from the station. That much we are sure. If it evaluates to true, we are sure that train is T0 is there in S0 to S something. Okay. Now what I do then I can say, okay, I can reach S0 to S1 using T0. So similar to the path example that we did, right? I have already taken the train from S0 to S1. Now let me continue my journey from this new station S1.
Okay.
Right. So that's why I'm asking a different question. I know that S1 is reachable from S0. Now I'm asking, is S4 reachable from S1? So this becomes S1 comma S4. Earlier it was S0 comma S4.
Yes.
I have figured out I can reach S1 from S0. So I ask, is S4 reachable from S1?
So we won't be updating the end station, right? We will just be updating the that is start station. We will just keep on checking for that.
Yeah. We'll only change the start station. End is fixed. Right. So are the others now convinced about this particular argument, what we are doing? Is there anyone who's still doubtful?
So once we get to S1, we will again check that if train T0 is present, right?
Exactly. That's what this is, right? It's reachable of graph comma T0 comma, instead of S0, we'll check S1 comma S4. Because we have already come to S1.
Yeah. After getting to S1, I'm saying, after getting to S1 also, we will check if T0 is present.
Exactly, yeah. So there you'll run a different call, right? You'll in that call also you'll check if T0 is there. So again, the same call is key of graph of start. Start here will be what? S1, because you are calling that function with S1, right? So you'll check S1 to S4. Now we'll start checking S1 to S4, S1 to S2. In which of them T0 is there, you'll keep checking that.
Okay, sir.
Now we'll move to S4, right? Now we'll move to S4. What happens now?
It will call for check for if some column
Train
has that
zero.
value T0. Then it will call for S3. S3 will be updated for that.
Okay. Now assume we want to find if T0 is there on the path from S0 to S4, right? So what will be how will this recursion end?
We'll check whether we have reached the end station or not.
How will we check that?
Okay.
What will be the base case?
If start equals to end,
Right.
There won't be any more outgoing edges.
return
C
true.
equal to end. We
If
are
start
checking.
equal to end, return true.
Yeah, not C equal to n, start equal to n, right? So if you have come to the station, see what happened here.
C is getting updated with the start, right? So C will be having the latest start station. So we need to check with the C.
Correct, but start of C. So start was what? S0, right? So we said S0, comma C, right? So S0 to C became S1 here, right? So what we ended up calling graph train S1, S4. Right?
That will become the new start.
Calling graph train S4, S4.
Yes, sir.
Right? So C is getting updated, but this is what? C is actually start. C stands for start.
Yes.
Right? So you'll end up checking if end is equal to start.
Yeah.
That you return true. And so why is this return false there? Suddenly it appeared. So why is that true? Why should I add that return false there?
So if it's not
If there is
equal
no
to
train at
and
the-
there is no train, then it will be return false.
Yeah, if there is no train, if there is no
And it's
start,
not the
right?
yeah.
For example,
Is false, yeah.
S0 to S4 and let's say T7, right? So from S0, no matter where you look, T7 is not at all there, right? So this will keep looking and then it will end up having to return false, right? You have to return false, no other goal. Okay, so is this reachability idea clear?
Yes, sir.
Yes, sir.
Let's move on now.
So
Yeah.
end equals to start. Can you tell how? Because I'm seeing that where the out degree is ending, then our code is ending, right?
So you mean S2, something like S2 having
Yes.
something.
Yes.
It need
But
not
you'll-
be S2, right?
We are not going to S0 again, right?
But you'll call for S2 once again to check whether it's the end station is equal to start station or not.
Or
You
you
have to
might
call
do
for
some
S2.
other intermediate station also.
You understand it like this, right? So you are in every recursive call, you are getting one step closer and closer to your destination. Right? Initially your destination is always fixed. So it was initial call was S0, S4. Then you move one step closer. So it was S1, S4. Next it will be S4, S4, right? Now you can't go anywhere. You have already reached. So you have to terminate.
Okay, so we are already saying that we have to go till S4 only.
Yeah. So if end is S4, then we can go only till S4, right?
Okay.
So it depends on end, right? That's why it's end is double equal to start.
Okay, so I'm still not getting end is equal to start. We are saying what is
It's just saying that if the end station is actually the station that we're starting with for that particular procedure.
okay. Okay.
Yeah. So the best way is if you can execute it. If you can execute it manually, you will see that it's not too hard, right? So it's just a matter of running it for a particular example, and then you will be convinced.
Okay. Okay, sir, I got it.
Okay, so we'll move on now to the travel time, right? So let's say you take the train T0 and you want to find out how long it takes to reach S2 from S0, right? S2 to S0, S0 to S2, how long it takes. Okay, so it's like slightly big code, but yeah. So I'll just quickly go over this in the interest of time. Now, see, because we have already written this reachable function, right? You are going to ask this question: if S0 is not S2 is not reachable from S0 using a particular train, then it will take infinite time to reach it, right?
Yes,
I mean, you never reach. So that's what I denote by infinity, right? If you have no train, if this particular train is not going to take you from S0 to S2, then there is no point computing the travel time. So the travel time is going to be infinity. Okay, so or a very large number. On the other hand, if it is reachable, then you have a finite time and you can compute. How do we do that? This is how we do it, right? So while you have not reached the destination, right? While you have not reached the destination, what do? You go through all the nodes, all the stations that are connected to you, right? You look at all the stations that are connected to you, and you look at that station where this train is. Okay, so you're starting from S0 and you're looking at S1 and S2, right? So you see where T0 is there. So T0 is there in S1. So C equal to S1, that is where T0 lies. So if that, once you find that particular station C, okay, you say that that's the next station that I have to move to, and you exit the loop. Okay, now once you exit the loop, what will be the time taken to move from S0 to S1? How will you compute?
S0, S1, T0.
Correct, right? So it is current time plus graph of start station to next station, and in that station, you look at how much time it takes for this train. That is 2, right? So key is T0, that is train. Value is the time taken. Now, is this clear what we have done? Or is it too complex?
Little bit complex, sir.
Okay, right. So let's go back. This reachability is clear, right? If it's not reachable, it's infinity. You cannot.
Sir.
Now what you do is start is not equal to n. Again, same logic. You are starting at S0, end is S2, right? So start is not equal to n. So here is what maybe I didn't mention properly. Can this train T0 appear in 2 edges?
Yes, sir.
How do you know? How do you know which edge to choose? See, this is maybe I should have mentioned it as a part of the problem. The same train cannot see if you have, let's say, say a Bangalore Delhi Express, assuming that there's a train connecting these two.
On different days, it can go to.
It can, but assume that.
Here it is not the case, not different.
Yeah, this is S0 is Delhi, this is Bangalore. Now
on the same day, it cannot go to different places from single.
So you cannot have the same train go through some random path and then other path.
Yeah,
so,
it is possible.
Right. So I am assuming here that this, if you have T0, it will only go in one of the outgoing
directions.
One direction.
Right. So that is an assumption. Maybe I should have mentioned that. Right. So now what you do is you look at all possible stations leaving out of S0. Right. There are 3 stations: S1, S4, S2.
Okay.
Okay. That is what this loop is for. Now you look at which station, okay, has T0 as a connecting train. Okay, which station? So is train a key in this graph, in this edge? Okay, that is what it means, right?
Start represent S0, C is the train T0, and
is the station S1.
C is the station S1.
C is station S1.
Yeah, so start C. So S0 to S1 is train present in, is T0 present in that path.
Okay, sir.
Okay, now you look at which path, you look at which station rather takes S0 to S1, or which train takes me, again it's very tough, right? So which station has T0 taking it from S0 to S1?
Okay.
In this case, it is S1, right? So it is S1 here because S2 doesn't have T0, S4 doesn't have T0, only S1 has T0 in it.
Yes, sir.
Okay, then you exit the loop. So once you find out which station is taking you to S1 using T0, you stop.
Okay.
Okay, now what you do? You know that start to next by using train is going to take 2 hours. That's what this thing is.
Yes, sir.
Okay, and then you add it to the total time take. Now, So far, so good, right? Now, what is the last step? There is one more step which is missing.
So we still not reached to the S2.
Correct. How do you reach to S2?
Then from S1 we have to check in the same train where we will go.
Correct. Yeah, that's correct. But so for that, what statement you have to write here? Once again, if you run this code, if you run this loop, it should work out fine, right? So what is your start station?
Start station is S1.
Okay. In terms of the variable, what is it?
C.
C, sir.
Yeah.
Which is updated in next.
So next is a new. So next station is your new start station, right?
Oh yes, sir. Start is equal to next, right?
Okay. So that's your new start station, and you once again know start, right? So I think now you may understand why start should be if start is equal to end, you have reached S4.
Oh, right, sir.
Right. So if start is equal to say S2 in this case, right? So start, you keep doing this. So S0 will become S1, S1 will become S4, then S4 will become S3. Finally,
S3 become S2.
S2, right? When S3 becomes S2, when start becomes end, you have reached your destination. Therefore, you get out of the loop, you return the time.
Yeah, at the last station, it is like S2 is equal to S2, then we will not proceed in this.
Yeah. Okay. So I hope that is clear.
Yes, sir.
Okay.
Clear. Thank you.
Here is the last question for the session now. So we have to find not the last, actually there's one more anyway. So we'll see. Find the quickest train from S0 to S2. There are like multiple trains, right? So for example, you can take T2, it takes 15 hours. You can take T0, right? T0 will take you through all these things, and it's the sum of all these times. You can also go from S0 to S1 to S2 using T1. Right?
Like we calculated the time for in previous code, we can store in the dictionary, right? So like T0 is taking 2 hours and much more. Then we will also store T2 is taking 15 hours. Then we will compare which is the quickest train.
Basic idea, right? You are right. So that's the basic idea. So instead of using a dictionary, I'm just using, implicitly doing it. So assume that the minimum time is some large number, infinity. Right? This is what we usually do, right? If you want to find the minimum of a set of numbers, we assume that T min is very large. Okay. And we don't know what the train ID is. So we have to keep that as unknown. Now we look at all the stations surrounding S0 and look at every train. Now we have to look at every possible train that could take us from S0 to S2. Right? So for each train that connects start station to C, it could be any station. Right? You look at the travel time of this train from start to end. Okay.
Yes, sir.
We are interested in all those trains which start from S0, right? Start station, and look at all those which can reach the end station. Now, if that time is less than the minimum time, then you update the minimum time, and you also update the train which will take you in that minimum time.
Yes. We store the train ID, right, sir?
Now, here is one small piece of caution, right? If there is no station, if there is no train that can take you from start to end, then T minimum will remain infinity, right? So for example, if start is S2 and end is S0, there's no train that goes from S2 to S0. Right? In such an instance, what happens? You won't have any train, so you have to return, let's say, -1. If not, you return the train ID. Okay, is this clear? Was this too fast?
No. If the train is not going to S2, then we will return -1. If the train is going, then we will return the train TID.
Correct. The train TID, which will have the minimum time, transit time from S0 to S2. Okay. Anyone else who has? Is there anyone who has a problem with this question? Okay. So I'm assuming you are okay. And we look at the last question. Okay, so find the maximum transit time between any pair of consecutive stations. So for example, let's say S0, S1, right? That's a consecutive pair. Now you have to find the maximum time it takes to move from one station to the next station, right? Across the entire network, train network here. I think in this case, the answer is 13, right? It takes 13 hours to go from S1 to S2, right? You should not look at total time, sum of times, right? You need to just look at two nearby stations and see which of these values is highest.
Like we have to find from S0 to S1, 2.5 hours is the highest time, which the slowest train.
Yeah, the slowest train, but not just from S0 to S1, but between any pair, you have to find out the final number, right? There's a single number. So for example, in this entire network, T3 is, you can't call it the slowest train because, you know, S1 to S2 may be very long. The distance may be like huge.
T2 will be the slow.
Sorry. Correct. Yeah, not 13, 15 is the answer for this. Yeah.
We will keep a variable for max and the train ID, and we will check for each column and value what the value is. If the value is greater than the maximum, then it will update for the maximum and also the train ID.
Yeah, right. That is what we'll do. We'll do this triple nesting, right? So we'll have the maximum time. As since we are finding maximum, it's okay to start with 0, right? What we'll do is we look at each station. Okay, R is a station, C is a station. We look at every train in the station, right? Between these two. So, for example, S0 again. If R is S0 and C is S1, you have T0 and T1, right? You'll have two trains, right? So keys of graph of RC will be T0, T1. Now we will look at the time, right? So this is the time it takes from S0 to S1, which is graph of S0, S2, T0, right? So you look at T and see if it is greater than the maximum time. If it is greater, then you update it. You keep doing this. Finally, you will end up with
50. The maximum travel time.
Yeah. Okay, so that's all we have. I hope we were able to cover at least some of the important topics.
Sir, can you please share these slides?
Yeah, I'll upload them. I'll first upload them and then send out request a mail to be sent out to all of you.
Thank you, sir.
Yeah.
So I have problem in click part where you just I want to know just that click means it has some same property between two nodes, right?
Yeah, every pair of nodes in that thing will have the same property.
So your code is not clear. I was just watching the YouTube live stream right now.
Okay, which code? The code which asks you to find the click, is that the one?
So the code was not clear for me.
Okay, let me go to that click part. Is the click? Okay. Is this the graph is this the code you're talking about?
Yes, sir.
Okay, tell me which part is unclear.
So if R is not equal to C and graph RC is not equal to 1. So you are just checking like if I say 1, 2, graph 1, 2. You are just checking 1 and 2, not 2 and 1. Also, you should check 2 and 1, no?
Okay, so see, I'm asking you this question, right? Is 0, 1, 3, is this a click in the graph?
Yes, sir.
Right, so this is a click, right? Because 0 is connected to 1, 1 is connected to 3, 3 to 0, right? Every pair of nodes is connected.
Okay.
Right, so that is what you have to check. Is every pair of nodes C connected That's what you have to check.
Okay.
Not if C is like, not if 2 is connected to 1 or that. Okay, that's also a question you can ask, but 2 is not a part of C, right? So you don't need to bring in 2 here.
Okay, sir. So can you also explain the path code once, because I have some doubt.
Yeah. So path is what did the path came after the clique, right?
Yes,
It
yes.
came after clique, sir.
Yeah. So which part?
So can you explain N1 and if graph N1 and 2 from here?
Yeah. So see, you are asking if 1, 3, 2 is a path. Okay.
Okay.
So P is 1, 3, 2, right? P is the list 1, 3, 1, 3, 2.
Okay.
Now N1 is what? First of P, right?
First, yeah.
N1 is 1 and N2 is 3, right? Because
3.
of P is 3, 2.
3 and 2.
Of that rest of P is 3. So you're asking if there is an edge between 1 and 3. That's what you're doing here, right? If there is no edge between 1 and 3, then can 1, 3, 2 make a path?
No.
No, right? So you can't, if you can't even travel from 1 to 3, then no way you can call this a path, right? So if there is no edge between 1 and 3, then you return false.
Okay.
That's what you're doing. So this is what you're checking first. If there is no edge between the first 2 nodes in the list P, then you return false.
Okay.
Else, right? Else means what? If 1, 3 exists, right? The edge exists.
Yes, yes.
What do? You are no longer worried about 1, right? You can hop from 1 to 3, and now you are looking at 3
to 2.
Right? So you're asking, is there a path from 3, 2, right? So how do you do that? From 1, 3, 2, you want to go to 3, 2. So you do rest of P.
Yeah.
Right? So is therefore you passive thing, right? Is path of graph comma rest of P. That's what. And then you do it once more because there is an edge from 3 to 2. So you hop to 2. And when you have a single node, right? When you are on 2, you have already reached your destination. Right?
Okay.
So there is a path. So you just return true.
Okay. Okay, sir. So length P is less than equal to 1 means there is a path.
Yeah. I mean, so you will. So typically, path will not have one node, right? So path will have at least.
Yes. Yes.
So you will, if you start off with a path that has like several nodes in it, then you will have, because you're cutting away one node at a time, you will end up with a situation where there is only one node. And if you have reached that kind of a situation, then it means you have traveled that path. So there is a path. Right?
Okay.
So if you end up with a single node, then it means that there is a path. Therefore, you can confidently return true.
Okay, sir. Thank you.
Yeah. So, yeah, is there any question regarding what we covered today? If not, can we close the session?
Sir, from when previous paper discussion session will be start?
That will happen on Monday or Tuesday. Mostly Monday, Tuesday.
Okay, sir.
Okay, so yeah, so thanks for joining.
Thank you, sir.
Thank you, sir.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir,
Thank
I
you,
have a
sir.
simple confusion, sir. Can you explain?
Yeah, which one regarding what?
So it's general question, sir. Just simple. Let's take seconds, sir.
Okay.
So can share a screen, sir?
Regarding the slides or?
No, sir. General question from week assignment, sir.
Okay. Yeah, please go on.
Okay. I'm just sharing slides. Sir, can you enable my sharing screen?
If you can tell me assignment number, I can maybe check it out.
Okay. So week 5 graded assignment.
Oh, week 5. See, we'll do one thing, right? So week 5, so I think very soon we'll have 1 to 8 discussion. Right?
No,
So,
sir, and it's not it's just confusion that I occur in every question, sir.
okay, ask that question so that it's easier.
So there is a procedure. Okay.
Okay.
So procedure is perfect and this happening. And in last there is no return true. Then when this return true will return, because above this there is also return false, then I understand when that return false will happen. But I always get confused when the last one means above the imperfect there is return true, when this will return.
See, the return statement gets executed only once any procedure. Okay.
So can I say the procedure?
Yeah, you can, if it's possible to paste it in the chat, that will be very useful.
Okay.
There is a way to copy the text in the.
Yeah, I am copying. So this is.
Yeah.
In last there is return true is there. No?
1 second. Have you shared something?
What, sir?
You have shared. Let me once copy. Okay. You have copied this. Yeah. No, go on. Yeah. Are you able to see the screen? Hello.
Yes, sir.
Yeah. So
yes, sir.
you want to understand when this is executed.
Yes, sir. When this last one will return, and that's always get confused. Okay,
let's see what is this procedure even doing.
So it is just checking the unique letter in word.
Okay, so C is an empty list to begin with. You are going letter by letter. If A is the
Yes,
I in the word, now if A is in the list, then you are adding it to C, is it? Did you do that?
So my doubt is not this how to solve this question. My doubt is that when this type of pseudo code come in that last part is return true, when this return true will give value. This is my general confusion in all every question whenever I get.
If the return false is not executed at any stage in the while loop, then you will have to come to this return true.
So mean when while I is smaller than letter count will end, then it will be give return true.
No. So when you come out of this while loop, right? When will you come out of this while loop?
When there is no letter in the word, means no word.
When I is greater than x dot letter count, right? Meaning when you go beyond the size of the word, that is when you will exit the while loop, right?
Okay.
When you exit the while loop, you will end up with this statement. Okay. So that is when you return true, but you have to ask the question before that. At some iteration in the while loop, if you encounter return false.
Yeah, that is the confusion. If I return false, then what will happen?
That's all. You will terminate, right? So see, return statement is executed only once. There may be like multiple return statements in your code.
Okay.
For example, let me write the same procedure, not the same procedure, but some other procedure, right? Say do something. Now let's say you have return 1, you have returned true, you have returned 3. Right? So you have
and is perfect. Yeah, and do something or anything.
Now I call do something.
Okay.
Okay, now let's say A equal to do something. Now what do you think is the value of A?
So he will be return 1.
It's a 3.
A will be 3.
Why? A will not be 3, right? A will be 1.
Yeah, 1, return 1.
Right? So that's the way return works. Return is what? Return is something that
Okay,
is,
so sequence wise.
yeah, you read a function from or a procedure from the bottom. The moment you see a return statement and moment that statement gets executed, you have to just stop the procedure, get out of it, right? It's like emergency situation. Moment you see the alarm bells ringing, you get out of the office or school or whatever, right? So that's how you have to understand return. So moment you see a return statement getting executed, you have to exit the procedure. Now, important part is execution is only important, not just being there. So the sequence is not important, right? So here return false is before return true. That doesn't mean every time return false will happen.
No.
Right? So return, as you said, return true might happen if this else clause never gets activated, right? So in that case, return true will only happen.
If in the inside the while loop, the return will never be updated, then this will be give return true.
Yeah. So basically, the moment you come across a return statement and that gets executed, right? So moment this gets executed, then you are going to exit the procedure. You are not going to return true at all.
So okay. So if I get updated inside the while loop, then I will not come at the return in the bottom part.
Yeah. If this gets executed, you won't have to worry about this. In fact, you don't have to worry about any statement after that.
So I will be updated, no, sir. I plus one.
That's what no, I won't be
after
updated.
the while loop. Nothing will get in updated if inside the while loop in return updated. That's
no. See, it's not about return being inside or outside the while loop, right? So the moment you hit return false, right? So because for some reason A is not a member of C, right? If A is a member of C, then you are going to go in, right? If A is not a member of C, you will go to else part, right?
Okay.
Now what will happen? Return false will get executed. Now, moment this gets executed, you will exit the procedure. You will not even update I. Return is like how do I put it? Return is like what you are like suddenly jumping out of a car or whatever, right? So assume that you don't break your leg, that you suddenly jump out. When I say you, I don't mean you, right? So it's
okay.
Let's say you are going in a car and you jump out of the car.
Okay.
What happens? Do you worry about where the car went? No, right? So you have gone out of the car. Now the car may go wherever it wants to, or it's like, let's take a more benign example of.
Means if I get the return value, then I am not aware about anything.
Let's say you get down at a station and then the train goes away, right? You don't worry about where.
I will not worry about that.
You just want
so
to.
I think this will return true when member C is always true, then it will return true, no, sir.
So yeah,
A is always member of C, then it will return true.
Yeah, if A is always a member of C, then you will keep going inside this. See, I don't understand what this procedure is actually doing. What is it doing actually? Can you tell me the context of this question?
Okay. So question is, a word is said to be perfect if no letter is repeated, and let is perfect via procedure that takes a row X in words table as input and returns true if the word in the row X is perfect word. Otherwise, return false. Then this is the correct procedure to choose an option which will be correct.
Okay, perfect means no letter is repeated, is it?
Yes, sir.
Okay, so you're starting at the first letter. So if A is in C, how will A be in C, right? First A.
So that's one the wrong answer. This will be the wrong, right answer. I just pasted.
Oh, okay. That's what I was saying. Like this code didn't make sense at all.
No, so my doubt was not this particular question. My doubt is that whenever I got return true in the last, now return false, then I got confused. Then when this part will execute, when this part will be updated. The question.
Yeah, this is the correct This is the correct solution, right?
I pasted, sir. Now correct solution.
Yeah. Okay, so what is it saying?
Yeah, this one is correct solution.
Okay, so if the first letter is there in C,
and if is this asking a letter is unique inside the word or a letter is unique in throughout the whole word data set?
No, it's only asking you for a particular word, right? It's looking at X dot word, yeah. See, the to begin with, let's take an example, right? Let's say word is great, right?
Okay.
So what are you doing? You're looking at I equal to 1. So first letter is G. So C is empty to begin with, right? So C is the empty list. Now, is G present in C?
No.
No, right? So you
return false.
You won't return false, right? So you won't even enter, no? You'll enter only if G is present in C. What is member of C, G, right? So member of C, G is false, right?
False.
So you won't even enter this if condition. So you will go and add A to C. So now G to C. So C will become G now. Now you will again loop, and then you will see if R is there in C. R is also not there in C. So you'll keep doing this. You will keep adding one letter at a time, and finally you will go beyond the letter count, right? At that time you'll exit the while loop and you will return true. So in this case, if you have a word like great where there is no repetition, you will return true.
So if you take I means there are repetition.
Yeah, if you take a word like good, right? So then C will again be empty list. Now G will be
first one,
first letter, right? So you'll add G because it's.
So then O.
Yeah, you will also add O because.
And then now.
So you will ask, is O a member of C? Yes, O is a member of C. Therefore, you will return false.
False. Okay.
And then that's all. You won't execute else, I plus 1, all that you won't execute.
Okay.
Or return true also for that matter.
I will go to while again.
You won't go to while again, right? You will return false.
And that's the exit the procedure.
Yeah, you will. That's the procedure exit, right? So once
whenever I got false, then I will okay.
Yeah, you will.
So we can conclude this as the return true or return false in the bottom part will be when inside the value the return will be not updated. Or like something.
Executed, right? Always use the term
executed.
Right. So
executed. Okay, executed.
The return is at any point of time. If return something is executed, then that's the procedure's life is done, right? That's all. You will have nothing else to do with the procedure.
Okay.
Okay. Of course, this is different for. I mean, if you're talking about recursive procedure, then you will have to slightly different, right? Because you'll go back to some other function call, your procedure call, and then you'll get back to this. All that is that, but for now, this is the understanding, right?
Okay.
Okay. Yeah. So that's all I had. So thanks for.
Thank you, sir.
Yeah. Thanks.
Thank you, sir.
Yeah.
So there will be session for week 5 to 8 also.
Week 1 to 8, there'll be a session. I don't know when it's going to be held, but very soon.
Okay. Thank you, sir.
Yeah. Thank you.
Thank you, sir.